it's my pleasure to introduce our speaker, Armond Duwell, who is a professor of philosophy at the University of Montana. Armond works in the philosophy of physics, quantum information theory, and as well as quantum computing. But more recently, he has developed interests in the philosophy of scientific understanding, and he is in fact writing a book on the topic. Most important, or maybe equally important, he is a former student of the Department of History and Philosophy of Science here at Pitt, and also a former visiting fellow at the Center for Philosophy of Science. So we are doubly delighted to host him back. And today he will be talking about scientific understanding, possibilities for purposes. Not yet. All right. Give us a minute. We are because before I was chatting while it was live and realized it was probably not optimal to have a friendly discussions about random topics while the audience was listening. Don't feel that professional, really. We're live. Very good. All right, let's give people a minute or two to join us while the list of attendees is increasing. Then I will introduce the events as a center in the coming days, and then I'll introduce our speakers. All right. On Friday, we do not have a lunchtime talk, but we are welcoming Maya Goldenberg for a lecture in the annual lecture series at 3:30 in the Cathedral of Learning on the 10th floor. And Maya will be talking about myth busting or meaning making, public science communications, and the infodemic. On Tuesday next week, we do not have either a lunch talk at the center at noon, but we have another online event. It's going to be a debate between a philosopher and a neuroscientist, more precisely between Nick Shea and John Krakauer. And Nick and John will be talking about representations in neuroscience. You can find the link for this online event on the center's website if you go to our calendar. And the next in-person lunchtime talk is on March 1st and will be given by Arnon Levy, who is a senior visiting fellow at the center right now. And he will be talking about an understanding first view of explanation. So we're looking forward to all of these events and to see you either online or at the center. Today, it's my great pleasure to welcome back, in some sense, Armond Duwell. It's part of the Future Former Fellow series that we introduced a few years ago, where we're trying to bring back philosophers of science who have been at the center in the past to hear what they've been doing and what they're currently working on. Armond is a full professor in the Department of Philosophy at the University of Montana. He works, among other things, in the philosophy of physics. He's been working on quantum information. In fact, he has a nice paper a long time ago called Quantum Information Does Not Exist, a provocative title. He's also been working on quantum computing. More recently, he has extended his interest toward general philosophy of science with some important work on understanding. He is, in fact, working on a book on understanding, which should be hopefully at least fully drafted and shot by the end of this year, or maybe even earlier. We're really looking forward to reading this book. Among other things, so Armond has several connections to Pitt. I mean, as I mentioned already, he was a fellow at the center a few years ago, about a decade ago. But equally important, at least for us, is a graduate of the Department of History and Philosophy of Science here at Pitt. So we are delighted to welcome you back. And today you're going to be talking about problems and possibilities, a theory of scientific understanding. All right, floor is yours.
Okay, thank you, Edward. I'm going to share my screen so we can look at the slides together. All right. Can I confirm with you, Edward, that you're seeing the slides?
Yeah, it's working very well.
Okay, super. All right. First of all, thank you, Edward, for the warm introduction. I really appreciate it. I was lucky enough to be a center fellow in 2011 in the fall. I'd be remiss if I didn't recognize what a wonderful job John Norton did as host. He really did a fantastic job creating a sense of community among the fellows. It was just an absolutely lovely experience. And of course, if anybody has a chance to be a fellow, I highly recommend it. Okay, so today I'm going to be talking about work that I've been doing with Soisy-Levian on a theory of scientific understanding. So here's the problem. Extant views of scientific understanding fail to be suitably comprehensive, and they fail in at least one of two ways. First of all, they fail to countenance the relevant kinds of understanding. For example, a lot of analyses focus on explanatory understanding, but then they say nothing about non-explanatory understanding or even practical understanding that's so important to scientific practice. On the other hand, they might fail to countenance the relevant targets of scientific understanding. So obviously, phenomena is an important target of scientific understanding, but I think understanding scientific theories, for example, is really important, and it's another component that a lot of views just don't say anything about. So I'm going to solve that problem today with the view that I'm going to be articulating. So here's the plan for today. First, I want to just give you a motivation and sketch of the view. This is going to be kind of high level and sketchy. It gives you a general idea. And after we have the general idea, I want to walk you through some specifics. Today, I want to focus on understanding of phenomena. It's a good place to start because, of course, people have intuitions about this. They might have read things about it. And it's easy to teach you about stuff you've already thought about. That said, everything I'm going to be saying about phenomena can actually be carried over to other targets of understanding. And I'll kind of make a point of that in the talk. So the first thing I'll focus on is representational understanding of phenomena, which is and includes, I would say, explanatory representations of phenomena. So there'll be a connection there, but it won't be limited to explanatory understanding. In fact, I won't even mention it. But then I'll turn to other kinds of understanding that I think have a claim to be understanding about phenomena. One is understanding how to generate representations of phenomena. And there, I mean, not only generating data about phenomena, but data models and theories of phenomena as well. And then there's a final kind of understanding, which I think has a claim to being understanding of phenomena, and that's how to manifest and manipulate the phenomena. So we're going to cover all of those things today, and then I'll wrap it up. So let's get started. Let's turn to a motivation and sketch of the view. So before we get started, I want to mention that a lot of what has happened with my thoughts on understanding are really influenced by Wendy Parker's work on adequacy for purpose. I was reading a lot about ideals associated with representation, and her paper on adequacy for purpose really struck a chord, and the view, as you'll see, is highly influenced by Wendy's work. So I just wanted to give a nod to Wendy here. So scientific practice is purpose-oriented. There's nothing surprising about that. And with respect to purpose, I think you can run the gamut from grandiose purposes like developing a unified theory of gravitation and quantum phenomena, or it can be somewhat more modest, as we'll see. You might try to simply get an estimate of wolf abundances. Now, we achieve our purposes through coordinated activities. And these activities can be self-coordinated, or they can, of course, be coordinated in large groups, as we've seen with big science. Now, like everything else in life, we have constraints on how we might achieve our purposes. They, of course, might be epistemic, but they might be technological, they might be methodological, they might be temporal, they might be moral, so on and so forth. And we're going to characterize scientific problems as constrained purposes. Now, here's how it connects to forgive me. I want to give you an example problem. So I live in Montana, and one of the things that the state needs to do is to manage wolf populations. And the way you manage wolf populations, at least out here, is by choosing how many permits you release for hunting and trapping of wolves. And in order to get somewhat intelligent sense of how many of those things that you can release, you need a relatively accurate and precise estimate of wolf abundance. And then you need to do this on a yearly basis. And because these are state agencies that develop these estimates, there are certainly financial constraints. There's a lot of good things to do and not enough money to do them. Now, there are a lot of activities, of course, associated in achieving or solving this problem. You have to generate data about wolf abundances, you have to generate estimates from that data, and then finally, you need to use the estimate. And I want to emphasize there are many different ways to solve this problem, or many different possibilities for problem solution, depending on which combinations of things that you choose to do. All right, so let's connect this to understanding. We generate understanding through problem solving. I hope that's not controversial. Now, on the view that I want you to consider today, we think that different problems individuate different kinds of understanding. Now, that means that if you've got two different problems and you've got the same target of understanding, the understanding that one of those solutions of one of those problems generates might not be good enough for another kind of problem that you want to solve, even if it's the same target of understanding. This is very hand-wavy now, and I'll give you an example later. Subkinds of understanding are going to be individuated by different base actions that contribute to problem solutions. So with the wolf example that I've given you, we've considered a number of different kinds of actions. So gathering data, generating estimates from that data, representing. So those are the subkinds that I have in mind here. Understanding of a target is associated with actions that implicate the target or inferences about the target. So I say actions that implicate the target. The simplest example here is a manipulation of the phenomena. So that's a kind of practical understanding associated with the target, but it can also be inferences that you might make on the basis of your manipulations of a target. Okay. How does this work? Well, we'll choose a target of understanding associated with a scientific problem. And that target of understanding for today is going to be phenomena, but it need not be phenomena. It might be theories that you're going to use to solve the problem. It might be the problem itself, which is the target of understanding. There's a lot of flexibility here. Now, once you choose a target of understanding, your understanding is generated in one of three ways. It's associated with your actions that implicate the target, or reflections on and comparisons between different ways of solving your problem, and then evaluations. I'm going to say more about each one of these three things right now. So, with respect to a base action, understandings associated with an exercised and enduring competence to perform an action that implicates the target of understanding and can contribute to a problem solution. Okay, now I'm going to just mention here, I will unpack that sort of stuff when we get to the next question or next section. This is just a high-level overview. We've mentioned some actions. Let me just emphasize them again. Manifesting and manipulating phenomena, generating data models, generating theories, and representing. So we have some understanding that's keyed into these actions and being able to do them. Next, we have reflective and comparative understanding. This is understanding that's associated with an exercised and enduring competence to reflect on or compare ways of performing actions to themselves or other things, and knowing some of the inferences supported by those reflections or comparisons about the target of understanding. And finally, evaluative understanding. That kind of understanding is associated with an exercised and enduring competence to compare the target of understanding to ways of acting and the problem, and knowing some of the inferences supported by those comparisons about the target of understanding. All right, so I know this is high level and a little hard to follow. Now we're going to turn to a specific example, which is going to help us explicate or try to draw out features of a particular analysis of representational understanding that I'm going to give now. Okay, so let's turn to representational understanding of phenomena. Right, so here's an example problem. Model planetary motion in the night sky to 16th century standards of accuracy and precision. And I want you to consider this in light of two different models, okay? One is the Copernican system, which of course you know well, and another is the Taconic system, which you may not know so well. You often hear about the Ptolemaic system here, and of course that was crucially important, but I want to use the Taconic system. So if you want to understand the Taconic system, kind of imagine you're God looking down at the Copernican system, and then you reach down and you grab the Earth and you hold it stationary, but then you preserve the relative motion in the system, okay? So in the Taconic system, you've got a stationary Earth, and you've got the sun and the other planets orbiting the Earth. Planets orbit the sun orbits the Earth. Now, one of the things that's really cool about the Taconic system is that all of the kind of telescopic evidence that Galileo generated to support the Copernican system can equally well support the Taconic system. For example, the phases of Venus come out right in both of these systems. Now, there are certainly important differences. You'll note, of course, in the Taconic system, you do not expect to see any stellar parallax, where, of course, in the Copernican system, you will, though it was centuries later when this was actually detected. Now, one of the things that I do want to draw your attention to is that the problem affords different possible explanations of retrograde motion. In the Copernican case, you know how this works. Retrograde motion is explained by the orderings of the planets and their periods, and then kind of line of sight claims with respect to the Earth, the planet, and the night sky. But in the Taconic system, what's interesting is you actually get an explanation of retrograde motion, which is a compounded circular motion explanation of retrograde motion. And the thing I want to emphasize about this is that with respect to the problem, these are live options. Okay, so let's take a look at an analysis of representational understanding of phenomena. Or at least this is a sketch right now. So one has some understanding of P of kind A, where A is the problem that identifies the kind of understanding that we have. One has some understanding of P of kind A via representing P if and only if, then there are going to come each of the three different subkinds of understanding. So I'm going to put each one of these different subkinds of understanding on a different slide, and we'll unpack each one of the conditions together. Base representational understanding. You have some base representational understanding if, and only if, one has an exercised and enduring competence to represent P adequate to the problem. So let's first unpack the notion of competence. This is Sosa's definition of competence. One possesses a competence if and only if one has the right constitution or possesses a certain skill. 2, is in the right conditions to perform an action skillfully. And 3, is in the right circumstances to succeed in that action. So the first clause is straightforward. You need to possess a certain kind of representational facility with a model. But of course, you need to be in the right conditions to perform that action skillfully. You can't be compromised by injury or illness or inebriation or what have you. And then you need to be in the right circumstances to succeed in that action, which in this case would mean something like you have the right calculational tools to get the job done. You pencil, paper, whatever you need, okay? Now, we require that the competence must be exercised. So, I think for representational understanding, this is really straightforward. You don't have any representational understanding of a target unless you've represented it. So that's all that condition is. Furthermore, the competence must be enduring. Now that is something that might be a little bit surprising, but I think it's important to include. So if you're going to claim base representational understanding, you need to have that enduring competence to represent. Now, let me make this kind of plausible to you. So I'll use myself as an example. It's been about 25 years since I've had a class on electromagnetism, and I didn't study it in grad school and really haven't had an occasion to return to it in my work. And I can tell you that I can't represent using that theory like I used to be able to. I have simply forgotten how to do it. At one point, I had some base representational understanding with the theory, and now I have very little. And that is true even if I might still remember some of the conclusions that I drew about systems using those representations. But that's different. Remembering some of the inferences associated with a representation is not the same as being able to use a representation to draw those inferences. So what this means is that base representational understanding can disappear over time. But I think that's just how it should be. We have all had instances where we used to remember how to draw certain kinds of conclusions, and we just have forgotten how to do that. I think your understanding fades in those cases. So that's why that is there. All right, now, let me emphasize, these guys have base representational understanding associated with those two models that I mentioned. But we don't have that, or it's unlikely that people watching this talk have that. We don't even know what the positions of the planets are in the night sky, much less be able to use these models to actually accurately predict where the planets in the night sky are. Instead, we have something different, right? We have a familiarity with the model, and we have a sense of how it works. And we can gain some understanding from that, but just not base representational understanding. It's going to be reflective and comparative representational understanding. So you have some reflective or comparative representational understanding if and only if you have an exercised and enduring competence to reflect on or compare those ways of representing P to themselves or other things. And you know about some of the inferences supported by those reflections or comparisons about P. So we've talked about exercised and enduring competencies. So let me say more about these things. So your understanding here is generated through knowledge of inferences gained from reflection. So if you reflect on the Copernican model of the solar system, you can draw inferences about the target of understanding. And you might say, oh, wow, so the planets have a certain kind of arrangement and not another. Retrograde motion is not intrinsic to their paths, but rather is a kind of artifact of line of sight, so on and so forth. So you can gain knowledge of some of the inferences associated with those models without you actually being able to represent the paths of the planets in the night sky as the problem demands. Now, you can also get knowledge of inferences from comparisons to other adequate representations. So here we might draw an inference based on a comparison between the Copernican model and the Tychonic model and say, oh, relative to the problem at hand, there are two different explanations of retrograde motion, which is pretty striking. And furthermore, it might be that the planets, have the Earth at the center of the universe versus something where, you have stellar parallax. Now, there's another kind of clause in this analysis that's important. Knowledge of inferences based on comparisons, not to different ways of representing P, but to other things. And that might be puzzling. But here's how to think about why that's here. So I take it it's completely uncontroversial that understanding of a target is associated with its properties and relations. Now, one way to discover relations that your target of understanding has is to compare representations of it to other things. And of course, you can come to know how things are related and hence gain understanding. Now, there's another important way in which comparison arises with respect to understanding, and that's through the use of foils. We use foils all the time to help us understand certain things. A foil is typically something that's either simple to understand, easy to understand, or it's something that we're quite familiar with. And by comparing and contrasting the familiar thing to the target of understanding, it can highlight important properties or relations that your target of understanding has. So that is why that particular thing is there. Now, there's one other thing that I want to emphasize here, which I think is quite important. Knowledge of inferences does not entail knowledge of a target's actual properties and relations. It just is knowledge of what inferences are possible given the constraints on representation that we had in virtue of the problem we're working on. Your representational understanding of a target will be factive only to the extent that your problem demands it. So in the case we're considering, model planetary motion in the night sky to 16th century standards, well, the representations that are used to solve that problem will only be guaranteed to tell you true things with respect to that problem constraint. It will not necessarily tell you true things about other stuff, like what the right explanation of retrograde motion is. So I do want to emphasize that knowledge is knowledge of inferences. All right, let's turn to evaluative understanding. All right, one has some evaluative representational understanding if and only if one has an exercised and enduring competence to compare P, phenomena, ways of representing the phenomena, and the problem, and knows some of the inferences supported by those comparisons about P that depend on P essentially. So it's a bit clunky, but it does get the job done. So what do I mean to compare P to ways of representing P, right? You might think that's kind of a contradictory thing to say, but it's not. So here's what I have in mind. Whenever you have a target of understanding, you have some means of sorting that target of understanding from alternative targets of understanding. And this constitutes, for the purposes of understanding, a kind of privileged characterization, which might be revisable. In the case we're thinking about, the privileged characterization of the paths of the planets in the night sky is going to be that quantitative description with respect to 16th century standards that you have. That's the thing that's going to be the target of understanding ultimately. But of course, you might revise that description based on more precise measurements, so on and so forth. Okay, but that's what I have in mind. You're going to compare that to ways of representing P, which of course we've seen are the different models that we've had, and then your problem constraints. Now there's also a requirement that P plays an essential role, okay? And here's an example that showcases why this is an important thing to say. We might have problem constraints that require us to only use scale models to represent the paths of the planets in the night sky, or something along these lines. And if we had that requirement, and we look and see that one of the ways that we're considering of representing the phenomena is a mathematical model or a computational model, and we say, oh, well, that's not an adequate representation of P, there you're rejecting that representation, not because it has anything to do with the target of understanding, but rather simply because it doesn't fit with problem constraints. If that demonstrates anything, it's understanding of problem constraints, not of the phenomena. So that's why that's there. So what does evaluative understanding tell you? Well, it tells you whether or not you've got an adequate way of representing the phenomenon. And it tells you where a representation might fail to meet certain constraints, where it succeeds in others, and perhaps even why it does so. Now, why would anybody be interested in this? Well, I think there are several things to say here. One of the most important things here is that, you know, it's not like problem solutions come advertised as problem solutions in science. You have to figure out if something's a reasonable solution to the problem that you have. And sometimes, you know, turns out that things that you think might work really don't. And here, I just want to mention no-go theorems. And, you know, the most famous no-go result of all is Bell's theorem, which says, look, if you want an empirically accurate representation of quantum systems, you can't get those with representations which are determinate and local. And that was, you know, mind-blowing, really shocking and amazing. And I think that's the kind of result that evaluative representational understanding we want to capture and characterize its epistemic value in that kind of way. All right, so I wanted to have a slide where just the whole view was kind of put there, but I didn't want to stick you with this and then go through it one by one. It's kind of overwhelming. All right, so that's just there for question and answer period. Let's mention some of the advantages that I think this view has. One of the things that I think is important here is heuristic value. So some people kind of mention that, you know, scientific understanding has some heuristic value. but they don't actually say how or why it has heuristic value. So I want to say something about that. But I also want to issue a kind of disclaimer. Given how kind of slippery heuristic value is, the connections I want to draw between heuristic value and the view of understanding that I just mentioned will be equally slippery. And I think that's fair. Okay, so first of all, comparisons can suggest new problems for consideration. So we've seen this, if we compare the Copernican and the Taconic systems, there's a new problem. Like, is there stellar parallax? Let's try to figure out if that's the case. So it certainly is heuristic in that kind of sense. Next, enduring competencies seem to underwrite abilities to use or generate new representations. The enduring competencies are representational competencies, reflective and comparative competencies, and then finally evaluative competencies. So look, one of the things that you might discover when you're generating understanding is you might see that you've got different ways of representing the problem, each which are perfectly adequate to what you're trying to do. And, but there are crucial differences between them. And you might think, hey, what can I learn from this? I might be able to learn what's possible, what's impossible, so on and so forth. But there are other things that you can do, and these are interesting, especially when you don't have adequate representations, when the representations you have fail in certain ways, and you know why one representation works for a certain part of the problem you want to solve, and another representation works for a different part of the problem, and you can do a couple different things here. One is you can revise your representational practices so that you have, a good sense about what you should take from certain representations and where you should just not try to use them. But then there are also opportunities for possibly creating, hybrid representations, which, take the good stuff from one, the good stuff from another, and try to fit them together. I know that's very hand-wavy, but I think that's kind of the way this stuff works. And then finally, if you've got no-go theorems, every no-go theorem, of course, has assumptions. And if you violate one of the assumptions, then the no-go result isn't in place. And, you could try something like this. So for Bell's theorem, you can try non-local theories. And we have, that's Bohm's theory. And you could try indeterminate or non-determinate theories like many worlds. And we've done that. So those are ways in which understanding can have heuristic value. Now, here are some additional advantages that I want to mention. The problems and possibilities view countenances all kinds of representational understanding. I didn't say anything about restricting to explanatory understanding, so that's there. We can also talk about objectual understanding on the view. Instead of having P represent a phenomenon, you can have it simply represent a domain, as they like to say when they talk about objectual understanding. No problem. Now, what about multiple targets? Well, I didn't say much here, but if you want to switch targets, all you need to do with the analysis above is switch P out for something else, which might be T, which gives you representational understanding of a theory. I didn't go into that, but you can do that. So we've got good coverage here. And as I have already emphasized, but I really do think that this is a key feature, not a bug, that understanding as we've characterized it is good enough for a problem. And it doesn't have to be absolute or unrevisable in order to achieve understanding. Those kinds of views make scientific understanding elusive, and I think that's the wrong way to go. As we've seen, understanding provides modal information about a target's relative to a problem, not just knowledge of absolute properties and relations or possessed properties and relations. Okay, So that was representational understanding. I know that it's was a lot of detail there. I won't be so detailed because you guys have got the idea now as I go through the other examples. It occurred to me that since this talk is on Zoom, you guys might need a mental break, so I'm going to tell a brief joke. It's one of my favorites. Why don't you see elephants hiding in trees? It's because they're so damn good at it. All right, with that pause, let's get back to the case at hand. Now I want to talk about understanding how to generate representations of P. And again, I have in mind here generating data about P, generating estimates about P, and even generating theories about P. I aim to have my analysis cover all of those things. All right, so let's take a look. Back to wolves. So one of the ways that scientists generate estimates of wolf abundance is that they tag wolves with radio collars. They capture them and then they recapture them. They detect them again with radio collars. And these methods, capture recapture methods, are kind of the gold standard in ecology. If you can do them, that's really great. And by the way, I should say recapture is important because it allows you to estimate a probability for capture, and this is how you generate an estimate of abundance. But it's really difficult to use on wolves. Wolves are elusive. They have very large territories. There are not that many of them, and they've got big pointy teeth. So scientists are interested in finding ways to not do those kinds of things. I should mention they're also expensive to do these things. There are a lot of other means of generating data about wolf abundances, and all of these things listed here have been used. Now, the real fundamental question is, can any of these ways provide reasonably accurate and precise estimates? And of course, scientists are interested in doing these kinds of comparisons. So Osband et al. Compared radio telemetry methods, hunter surveys, and genetic sampling at rendezvous sites, wolf rendezvous sites, and combinations thereof, and tried to figure out what was something that could generate reasonably precise and accurate estimates. And one of the shocking results, was shocking to me, was that estimates based on hunter surveys alone provided the closest match to joint Idaho Department of Fish and Game and Nez Perce tribe estimates in 2010 and 2011. The Idaho DFG and Nez Perce tribe estimates were based significantly on radio telemetry data from wolves, but not exclusively there. So they were something like an epistemic standards. It's amazing that hunter surveys could possibly achieve any kind of reasonable estimate because hunters make mistakes. So one thing to say is it's really difficult to tell the difference between a wolf and a coyote at a distance, which of course is where hunters are seeing these things from. But not only that, there's no way to distinguish different individuals in these cases. So that's kind of fascinating. Now, I will say as a disclaimer, I know of no state agency which has adopted only hunter surveys as their means of gathering data about wolf abundances. Now, one of the things that we also see is that scientists are interested in evaluating possible problem solutions. And Creel provides a really nice formulation of a problem constraint, and I want to read that. Estimates of abundance must be based on data that were collected in a manner that matches the assumptions of the statistical model that is used to estimate population size and provides data that are representative of the broader population about which inferences are made. Now, that's just so well said, and in many ways so unbelievably obvious that you can't imagine that anybody would make an error like this. And yet, if we look at the estimates that Idaho's Department of Fish and Game generated for 2020, They were based on data from motion-activated camera traps at rendezvous sites, wolf rendezvous sites, either known rendezvous sites or predicted rendezvous sites. And they used a space to event model associated with Moeller et al. In 2018 to generate their estimates of abundance. Now, there are a number of assumptions associated with that model. Time and place of camera events are independent of animal locations. Detections must be independent in space and time. Area per camera must be measured for each camera. The landscape does not change detection probability. Now, every single one of those assumptions is violated. As for the independence assumptions, I mean, you used motion-activated traps, so the camera only takes pictures when wolves are present, and you did it at rendezvous sites. Not only that, area per camera wasn't measured, and the assumption that landscape does not change detection probability is, of course, a poor one. Of course, wolves are influenced by their landscapes, period. So, what's this all to say? Well, this is to set up a kind of idea that scientists generate certain kinds of understanding that I attempt to capture here. So, one has some understanding of P, of kind A, via generating representations of P, if and only if. One has an exercised and enduring competence to generate representations of P adequate to A. Now, one thing I do want to draw your attention to is that, as we've seen things play out here, there are certain people that are gathering data, there are other people that are generating the estimates. So we can attribute base representational understanding either to a group of people, if you like, or a more specialized base understanding to individuals. So you might associate it with generating data if, you were out tagging wolves, or of course, generating estimates if you were doing that, so on and so forth. So there's some flexibility here, and I like that understanding can be attributed not only to individuals, but to groups. One has an exercised and enduring competence to reflect on and compare ways of generating adequate representations of P to themselves or other things, and knows some of the inferences supported by those comparisons about P. Of course, in the Ausband case, the kind of surprising feature is that there are ways of generating estimates of wolf abundance from hunter surveys alone that seem to be reasonably accurate and precise. Amazing. And then if you have evaluative understanding, evaluative generational understanding, one has an exercised and enduring competence to compare P, ways of generating representations of P, A, and knows some of the inferences supported by those comparisons about P that depend on P essentially. What we learned from Creel is that there are certain ways of solving our problem that aren't actually ways of solving our problem. If you try to generate estimates in a way that violates the problem constraints, you're probably not going to end up with accurate estimates of wolf abundance. Full stop. All right. Now, some advantages. One of the things I want to just point out here, and this is perhaps a point that's more about the example than it is about this means of generating understanding, but I think it's an important point with respect to understanding generally, is that explanation is not the only important game in town. We know how to explain wolf abundance. It's actually pretty easy. It's food, it's weather, it's disease, and then it's predation. That's easy. What's hard is figuring out how many damn wolves there are. So I just want to emphasize that some scientific achievements just don't have anything to do with explanation. Instead, it's something else. And we need a theory of scientific understanding that can capture that. And like representational understanding, this is flexible in terms of actions or targets. So as you might have noticed in the conditions, we can think about different kinds of representations that we're generating. Are they data representations? Are they data models? Are they full-blown theories of phenomena? Doesn't matter. Any one of those fit into the conditions for understanding that I've given you. I should also mention, we also have the same kind of flexibility in terms of targets. We've talked about generating representations of phenomena, but you could just as well have generated new representations of theories as well. I won't say more about that, but you can do it. The same pattern just repeats over and over and over again. All right, so we're in the home stretch. I wanted to just draw your attention to one more kind of understanding, which I think is an important kind of scientific understanding. And that's understanding how to manifest and manipulate P. This is an example that Oscar Westerblad, who's a grad student at Cambridge, has used to, I think, very good effect to emphasize how important practical understanding is to science. That is understanding which doesn't necessarily have any kind of theoretical support structure, which is kind of directing our actions, so on and so forth. This is also something, of course, that Steinel has emphasized a great deal with exploratory experimentation and whatnot. So anyway, the episode that Oscar uses here, I'm just going to borrow. It's Ørsted's demonstration of electromagnetic effects. So you're probably familiar with this, so apologies if this is really boring for you, but let me just mention it. So let's go in the diagram from left to right here. We have three different kind of setups. And let's suppose that there's a wire, and let's just stipulate that that wire is running along magnetic north, and then there's a compass located to the left of the wire, and we'll turn on a current in that wire, and that needle will be deflected from magnetic north. And if we move the wire over the top of the compass, we see that the deflection from magnetic north is actually even stronger or even more pronounced. And then as that wire crosses over again, we'll see still a deflection from magnetic north, but it won't be as pronounced. Now, this sounds all innocuous, but Ørsted quite rightly points out this is pretty amazing. What this means is that the electromagnetic force can't be an attractive or repulsive force, because as that wire crossed over from one side to another, if it were an attractive or repulsive force, the deflection from magnetic north should have occurred in the opposite direction as it passed over. And of course it doesn't. Hence the big problem. Now, Ørsted did all sorts of other manipulations here. If we start at the upper left-hand corner of the screen, that's the kind of deflection that I just mentioned. And if we go in a clockwise fashion, we see that if we put that wire underneath the compass, it'll deflect from magnetic north in the opposite direction. And if we put the wire in the same plane as the compass and behind it, we see that the needle is now deflected down as opposed to just in the horizontal position from magnetic north, it goes down. If we flip that wire over and again keep it in the same plane as the compass, the needle will deflect up. Now this is the right-hand rule for electromagnetic force, which you guys all know well, but of course it was an amazing thing at the time. Now Ørsted did all sorts of other manipulations. He discussed putting various different material media between the wire and compass to see if there's any enhancement or diminution of the electromagnetic force, so on and so forth. Now, switching gears here, I also want to draw your attention to the fact that Ørsted has something along the lines of some constraints for his problem. So let me just read a little bit from the paper here. The first experiments respecting the subject, which I mean at present to explain, were made by me last winter while lecturing on electricity, galvanism, and magnetism in the university. It seemed demonstrated by these experiments that the magnetic needle was moved from its position by the galvanic apparatus, but that the galvanic circle must be complete and not open, which last method was tried in vain some years ago by very celebrated philosophers. But as these experiments were made with a feeble apparatus and were not therefore sufficiently conclusive, considering the importance of the subject, I associated myself with my friend Esmark to repeat and extend them by means of a very powerful mnemonic battery provided by us in common. Mr. Lugel, a knight of the Order of Danneberg, and at the head of the pilots, was present at and assisted in the experiments, so on and so forth. So, I mean, the kind of problem constraint he's mentioning here is just that if you want to demonstrate the existence of electromagnetic effects, they need to be obvious to the senses. And of course, if they're not, there's a problem, and it needs to be obvious to the senses, not only to one person, but other, epistemically respectable agents as well. All right, so with that example in mind, let's consider an analysis of understanding of P via manifesting and manipulating P. One has some understanding of P of kind A via manifesting and manipulating P if and only if one has an exercised and enduring competence to manifest or manipulate P adequate to A. Of course, Oersted had this. One has an exercised and enduring competence to reflect on or compare those ways of manifesting and manipulating P to themselves or other things, and knows some of the inferences supported by those reflections or comparisons about P. Oersted certainly had that. Because I manipulated things in this way, I can conclude the electromagnetic force is not an attractive or repulsive force. It's something entirely new, right? That was amazing. And then, of course, one imagines that he had, oh, excuse me, that's a typo. It should be evaluate, manifest, or manipulate. One has an exercise and enduring competence to compare P, ways of manifesting, manipulating P, A, knows some of the inferences supported by those comparisons about P that depend on P essentially. Well, of course, Oersted could say, hey, my way of doing it worked well. I could clearly demonstrate these effects. Okay, almost there. I just want to say a few things in conclusion. So, we started with a problem. Extant views are not suitably comprehensive or unified. They fail to countenance the relevant kinds of understanding, and they fail to countenance the relevant targets of understanding. Though I have focused on understanding phenomena, I've given you ways in which you can generalize this to other targets of understanding, and I've also showed how this isn't restricted to explanatory understanding, but other kinds of understanding are available. The problems and possibilities view of understanding is that understanding is generated through problem solving, and that we possess some understanding by having certain exercised and enduring competencies. And furthermore, we generate that understanding through different kinds of actions and competencies. And there's a triadic structure, which we see repeating again and again and again. Base action understanding, flexion and comparative understanding, and evaluative understanding. All right. I thank you very much for your attention. I am very keen on hearing some of your feedback. I'd love to address some of your concerns, and we can learn something together. So thank you so much.
Thank you very much for this lecture. So let me remind you how it is going to work for the Q&A. If you have a question, please go to the bottom of your screen, click on Q&A and just write your name there, and I will promote you to the status of panelist so that you can ask your question directly. If you are at the center right now, because some people were watching you at the center, you can just also do the same, write your name on the computer, and you should be able actually to directly jump in through Sam's window. All right, so giving people a few minutes to do that. While people are writing down their name, let me get started maybe with a question for you. I'd like to hear more a bit about the notion of a constraint and the way you're thinking about it. So in AI, as you probably know, let's say not the recent AI, but the more like 1990 AI. So there was all these models that were influential in psychology and in philosophy about soft constraints, where a constraint can be partly fulfilled, and there's always a tension between various constraints. Some can be fulfilled, and if you fulfill one constraint, you're unable to fulfill another constraint. So there's no assumption that somehow one is able to fulfill all the constraints to the same degree at the same time. That leads often to many equilibria, where in fact there are many ways to address the constraints provided, because you do different trade-offs, depending on which constraints you're using. So I'd like to know whether that's something that you are amenable to, or whether you have rather a conception of constraint that's much more rigid. It's either on and off. So yeah.
Yeah, no, so thank you for the question. No, constraints don't need to be hard and fast. I mean, oftentimes, perhaps a better way to say it is we've got a set of desiderata or something like this, which we might meet certain desiderata to certain degrees and others to others and so on and so forth. And, there's a balancing act there. So, and I mean, this touches on a few different kinds of things. I mean, first of all, rarely do we scientists take time to try to spell out what a problem is in gory detail, right? It's often tacit or implicit, and that's completely fine. So yeah, I think that's fine. The other thing I would say is that, Wendy kind of addressed this issue, Wendy Parker, in her paper on adequacy for purpose. Sometimes we can have a certain kind of preference structure over a purpose, and we can, partially achieve some of our purposes, and there's a ranking about, which purposes are more important than others, so on and so forth. So I think there's a lot of flexibility that can be had here to accommodate your concerns and make sure that it's, reasonably descriptive of scientific practice.
So I mean, but you'd be happy also with the consequences that, given a problem, a set of constraints, we might have different understandings, because we might have different equilibria between these constraints, different way to
Yeah,
satisfy them. So there
yeah,
might not be one single way. Given a problem, set of constraints, there might be actually different ways of understanding a given problem or phenomenon. Or is that
yeah.
something you'd be happy with?
Well, I think so. I mean, so the idea there would be you would have one problem which is rather vague, and then there might be certain precisifications of that problem. And but that seems fine with me. I don't see this as being especially problematic. And then of course, it's not like understanding gets attached to a particular problem here. The understanding might be good for several different kinds of problems, and that's fine too.
Cool. Arnon, if you could turn the camera on and turn the mic off from the computer, I would give you. So challenges of Zoom. JP, maybe give a hand to Arnon. Oscar, floor is yours while JP is solving the problem.
Hi, Oscar.
Hey, yeah, thanks very much for this. I mean, I'm really on board with what is being said. Thanks for the mention as well of the case. I guess my question is one about epistemic value, given the sort of pragmatic account that you're putting forward, where it seems like a lot of people who put emphasis on things like explanatory understanding or objectional understanding put particular value on those kinds of understanding because they are the final product of problem-solving activities or something like this. And so there's something about those products that we value more than simply being able to produce them. And I guess I worry about, or at least this is the sort of worries that I have thrown at me as well, with the pragmatic account of understanding, that it won't capture this kind of final value. And so I'm curious what you have to say about the issue of value in these cases and final value, and whether this sort of pragmatic understanding has anything more, say, than instrumental epistemic value.
Yeah, thank you for the question. So there are, I suppose, a few things to say. I mean, one thing that comes to mind is all this stuff contributes to a problem solution. So there's just clearly value there. But you could press me and you could say, well, yeah, okay. I mean, so, but, there might be, once we've got one way of solving the problem, why should we care about any of the other possibilities? And I mean, I would say to those people, well, you might care about them because of their heuristic value, like I mentioned. But I mean, I guess there's a sense in which, for whatever reason, you were interested in understanding a particular target, and there's more understanding to be had if you are willing to engage in these kinds of comparisons to other ways, so on and so forth. Now, I mean, I do think, though, that it's kind of pragmatic choice, right? I mean, there's nothing that demands that one just endlessly increase understanding, but the same is true of knowledge, right? I mean, we can always have more knowledge about something, but it's not always useful. So I guess perhaps this isn't a good answer to the question. If the demand is that understanding always has to be valuable, I think I would say that's just kind of a silly demand. It's just like knowledge doesn't always have to be valuable. Why would we think that understanding always has to be valuable? So that's off the top of my head, but I thank you for the challenge. I think that is an important thing that I'll have to think more about.
No, that's great. Thank you.
Thanks, Oscar, for joining us. Arnon, are you able to join us, or is it still a technical challenge? Yes, very good. Now we just need the sound.
Yeah.
Yeah, very good. Thanks.
You can see me, you can hear me. I know. Yeah. Thanks. That was very interesting. I'm sort of wondering, I mean, you spoke and you said that you wanted to give an account of a wide variety of forms of understanding, and that, understanding why, or explanatory understanding, was just one case. I have sort of the opposite kind of question, or sort of misunderstanding, I guess, and that's about what is being ruled out. Like, what kind of scientific achievement? I understand the sort of stuff that's being ruled out because it's not good enough to count as, like, on the scales that you mentioned. But what sort of achievement would be ruled out? It seems like a lot of stuff that ordinarily, maybe just because of the use of the term, I would not want to describe in terms of understanding is included here, including a lot of experimental work, a lot of, for lack of a better term, more sort of material, concrete work. Are you happy to include all of that under understanding?
Yeah, so I mean, people like Oscar have convinced me that, there are really different targets. Well, okay, let me just mention this. Epistemologists distinguish between a kind of intellectual or theoretical understanding, where the target of understanding is a kind of proposition, or it may be the phenomena, and they distinguish that between understanding of practical actions. Oscar has used the example of playing guitar, right? If you understand how to play guitar, you can play the guitar well. Well, it's also the case that a hell of a lot of scientific activity involves, skilled action. And we should associate understanding of actions associated with that activity. So from your eyes, it suggests that I'm not getting what you were trying to tell me. So help me.
No, I'm just trying to understand. I guess I'm trying to understand if I'm very skilled at using some instrument, a microscope, or I can see why there would be explanatory understanding, at least in some cases, presupposed by that. But if we kind of bracket that, so do you want to consider just the sort of the sheer skill of using the instrument as a form of understanding?
Yes, I do. Yes, I do. And it's not necessarily explanatory at all, of course. I mean,
Okay.
it's in many ways the wrong target, right? I mean, so actions aren't typically targets of explanation, usually propositions or phenomena are.
So would you then agree that a lot of the work would then have to be done in terms of distinguishing different kinds of understanding? Because we would still want to say that that's a pretty different scientific achievement relative to explaining something, relative to experimenting. So then it looks like the notion of understanding is being expanded, but then a lot of stuff that didn't used to be counted as understanding needs to come in to distinguish different forms of understanding. Is that?
Yeah, I mean, this is, the view I'm advocating does not make scientific understanding elusive. It is widespread. Some of it's very hard earned. Some of it is cheap, like the ability to use a microscope, right? So yeah, I'm embracing that.
Okay, thanks.
Thank you.
John, floor is yours. Thanks.
Ari, can you hear me?
I can. Hi, John.
Ari, it's love you to see you and love you to hear from you. It's been a while. I hope the background here is making you feel a little nostalgic.
Yes, but Edward already told me it can't possibly be real because it's very cloudy. Oh, no, it's very sunny. I'm just mixing it up. Maybe that is a live shot. No.
Yeah, it's not live. It's a photo I took with my cell phone and camera when I went for a jog. Okay. So here's the question. It's sort of got a whole bunch of bits in it, but the basic idea is this. You've given us a new gadget, right? So what we want to do is play with it, right? So I want to know what can I now do with this? And I've got 3 possible applications. Maybe they're already in there and I just didn't notice. And they're increasingly complicated. So can we go through them and then see what you think? So the first one is, we often think we get better understanding from analogical models, which are just wrong, right? I mean, the classic example would be, if you want to understand a simple field theory, you can model it as streamlines of flow in a fluid, and you can, and you get the inverse square law out pretty easily because the streamlines spread out nicely. But notice the representation is essentially false, but it's very helpful. First one. Second one, is there a notion of comparative understanding? So when we look at your example of Copernicus and Tycho, you talked about understanding within each of the theories, but there's also a sense that we now have, maybe incorrect, but we now have that we understand the phenomena better with the Copernican theory. So it's now, so it's false models, a comparative notion of understanding, and then the third one is a branch of understanding that comes up fairly often. Again, it might have been in your account, and that's in mathematics. I know this is now getting a little far from where you started, but people designate some proofs of theorems as being explanatory or helpful, proofs that give you a kind of understanding that you don't get with other proofs. An example, even though there are over 100 proofs of Pythagoras' theorem, one that I happen to like simply uses similar triangles. You start with the original triangle, and then you make smaller copies that are similar to the original, right? And out of that, you can produce a proof of Pythagoras' theorem. That gives you a wonderful grip, because you immediately realize that Pythagoras' theorem is going to fail in any space that doesn't admit similar triangles that are not congruent. So the surface of a sphere, immediately you know it's not going to work. And immediately you know that you're going to get closer and closer to it working if you get yourself into a smaller and smaller realm. All of that you do without any calculation. You just see the proof depends on similar but non-congruent triangles, and you know that many other spaces don't allow it. So it's false models, comparative notion, and understanding, proofs in mathematics that give you better understanding versus those that don't.
Yeah, thanks. Okay, I hope I can do justice to all of your questions. So, I mean, if people say that they have better understanding from analogical models, I mean, the question is, what is it that they've they think gives them better understanding. So, I mean, what I would say is that some representations are easier to get a mental grip on than others. And we can prefer them for those reasons. But just because something is easier to get a mental grip on doesn't mean it's going to give you a solution to the problem you're interested in. In fact, it might mislead you. So, you know, I think that's what's going on. You just have to distinguish between certain representations being easier to kind of cognitively bring on board and maybe mentally manipulate, especially without calculations. Um, but but those just aren't adequate to a lot of problems that we have. So I would say that, you know, the feeling of understanding and understanding are not the same thing, and that's probably what's going on in that case. So I'll go through all of these, and then if I'm not getting what you're saying here, then you'll please correct me. So comparative understanding, right? So this is actually, I think, quite easy to fit into the framework. So when you say something like Copernican understanding gives us, or excuse me, the Copernican model gives us better understanding than the Taconic model, I would say, well, yeah, what you mean is if we have an updated problem, which requires us to, you know, make sure we get stellar parallax right, then yeah, clearly the Copernican view gets something right that the other view doesn't. So that's one way to say it. Yeah, I mean, one way to fit it in the framework is to say, okay, well, I mean, the problems that we're interested in solving change over time with new empirical data, and of course they do. There's another way to fit this into the framework, and it's to change the problem constraints, right? So you could define a kind of understanding whereby the inferences that you generate with your representations have to be true. So you could also bring that kind of intuition in that way in our framework. So two different ways I think we can accommodate that. Now, with respect to the, you know, especially illuminating proof. So I mean, I think what you were saying there is exactly, you know, what the solution needs to be. So certain kinds of proofs upon reflection can generate important inferences in easy ways that other kinds of demonstrations can't. So you mentioned it, right? So we see that because it depends on congruent triangles, this isn't going to work with a different topology. So it's precisely because you've reflected on that method of proof and you draw inferences about it that you have some understanding that might not be accessible with a different kind of proof. You can draw some inferences, but not those. So that's why that proof might be superior with respect to understanding. So I think there's room there to capture that intuition.
Yeah. Can I say something more, or is it okay? Yeah, no, all sounds good. I want to go back to the second example of comparative understanding. You're certainly correct that if one theory is empirically better than another theory, it gets a leg up, and you know we're going to be happier with that theory, and maybe say we understand better. But there's but in that astronomical example, there's a sense in which we get a better understanding without there being an empirical difference. This is one of the arguments that Copernicus used against the geocentric theory. Even if you coarsen out both geocentric and heliocentric theories so that they are empirically equivalent, right? I mean, that's a, you know, that's throwing away a lot that matters. But even if you do that, there's a sense in which the Copernican theory does a better job of explaining the retrograde motion of the planets than does the Ptolemaic theory. The Ptolemaic theory depends upon a massive coincidence that all of the motions on the epicycles and deferents are perfectly coordinated with the motion of the sun, and there seems to be no reason for that other than just it's a brute fact. Copernicus very happily can point out no, in my theory no such coincidences are needed. Now, so what's going on there? Maybe it's an illusion. You know, maybe we're just being tricked rhetorically by Copernicus or the defenders of the heliocentric system have point that out. Or maybe there's something more going on, so that we genuinely can say that that we get a better understanding of the problem of the planets from the Copernican system. Does that make sense?
Yeah, it makes sense. I mean, look, we think one provides a true explanation and the other one doesn't. I mean, isn't that what you're saying there?
True is actually the word that was used, interestingly enough. I think it was Osiander in his preface used it, but I think he used it to mean more accurate. Sorry, it was just a tangent. At the time when Copernicus was debating the geocentrists, right, of course, that was the issue, whether the Copernican theory was the true theory or the one that represented the truth better than the Ptolemaic. And he was using the elimination of arbitrariness as an argument for that. So I'd flip it the other way around.
Okay.
Well, I mean, what's happening here is there are other considerations coming in. So there's, you know, this is a classic example of an inference from parsimony, right? Copernicus needs fewer independent assumptions, right? And if you have fewer independent assumptions, do you understand better? Maybe, but as a principle, it's a very dangerous one, because in the evolution creation debate, the theist will tell you they have one assumption: God, right? You know, so maybe counting hypotheses is risky.
Yeah, I mean, it's not clear to me that, I mean, I don't really get the sense, and I'm not trying to be deliberately stupid here, but I don't really see how there's different number of independent assumptions between the Tychonic model and the Copernican model. I mean, it's just the orbit of the planets and the periods and lines of sight. It's exactly the same. So I mean, comparing parsimony here, I don't really see a clear winner. But in any case, well, I mean, we should set that to aside. So is there a question, is there something that can be said here about having fewer independent assumptions as being a signal for understanding? And I think I've thought about this, and I think the answer is no. It doesn't actually give you better understanding. What you can say is that sometimes when there are fewer independent assumptions, it's easier to take on board a representation, easier to deploy it, so on and so forth. But that, for me, is about ease of understanding. It's not about the kind of like total amount of understanding or something like that. So I think I would respond to your intuition that way. And I would also just point out, I don't think it's true that fewer assumptions always give you better understanding. So one quick example there is, let's see if memory serves me correctly, and it might not, so apologies in the room, but I think Birkhoff has an axiomatization of Euclidean geometry, and it's relatively inscrutable compared to the regular old Euclidean axiomatization. So fewer assumptions does not mean easier to understand. All right, thank you so much for your comments, John. Really appreciate it.
Thanks, John, for joining us. Musa, do you think you can try to join us through the centers? Yes?
Hey.
Very good. Thank you.
All right.
Hi there.
Perfect. Can you hear me? Okay, good. Thank you so much, Armond, for the talk. So I think, I mean, I want to ask a question. I think that you partially answered partially to your response to John. But so you mentioned that, you know, your theory of understanding can be also applied not just to phenomena, but to other targets for understanding, like theories, for instance. So I was wondering if there is a kind of, I don't know, conflation in when we talk about the understanding of a theory. because one way of understanding a theory is like, when I just sign up for a course in physics and then the professor just tries to, help me to understand Newtonian mechanics. But there is another way that, when we talk about understanding a theory, and that is basically understanding through the theory. So the target here doesn't seem to be the theory itself, but what theory actually is targeting. So I was wondering if we make this distinction between two ways of understanding a theory, whether, for instance, understanding as competence can be again applied to both cases, or is it like a kind of understanding that can be only applied to understanding theory rather than understanding through theory? And for instance, to make it a little bit clear, hopefully, is think about, I know, a theory about Big Bang. There is no way that we can reproduce the data. There is no way that we can really create the phenomena in any direct way. But we think at least that, we have a pretty good theoretical understanding, at least of some aspects of that phenomena. Thank you so much.
Yeah, thank you so much for the question. Yeah, so when we think about theories, there's a distinction that I like to make, and it's between the understanding of a theory that we have, which is in some sense independent of its representational uses, and then the understanding of the theory that we have, which is dependent on its uses. So I think the former, understanding the theory that's independent of its representational uses, is something that people just don't talk about in the literature. Henk de Richt focuses on the use of a theory, being able to deploy the representational resources of a theory. That is what understanding a theory means. And I'm completely on board with that. That's right. It's just an incomplete view. So we need a theory of understanding that can target both of those aspects of things. And I think, the kind of deep understanding the theory is that's independent of its representational resources. These are the kinds of things that, people like Rob Clifton and Itamar Potowski had of quantum theory. Like, they just knew that structure and they knew it inside and out, and they were very effective at manipulating that structure. So that's the kind of understanding that I think people don't say or talk about enough, that I want to make room for. As well as, the stuff that you mentioned, the use of a theory, that's also critical there. So, and it's interesting, these two things will fit together in interesting ways. Having understanding of one kind will promote understanding of another kind, so on and so forth. Did I address your question? Okay, thank you very much. I can't hear you.
Good catch. We have 1 minute. If there's an urgent question, is there someone from the center or someone among the attendees? No. Let me just double check. I'm not missing anyone. No, that seems fine. Anyway, so we're reaching the end anyway, nearly 1:30. So thanks for joining us for this lecture. Thanks again to you, Armond. It's been really a great talk, and we're really looking forward to the book, actually. Hopefully early next year. Maybe more than us.
Thank you for everybody. I really appreciate your feedback, and I'm sure I will benefit tremendously when I try to incorporate your thoughts into what I'm working on. So thanks again. Really a pleasure to be here. Look forward to seeing everybody soon.
All right. See you online next week to the debate between Nick Shea and John Krakauer. All right. Take care, guys. Bye.